in Poincare group, some related group has several components.
4 components, yeah.
Yeah, and I understand the statement of the theorem to say that whatever symmetry you have acts as non-symmetry, there's another set of components that acts complex conjugate way, antilinearly in Lorentzian.
Yes.
So what are you saying is the Wick rotation?
Well, so there's a proof of that, right? So in Lorentzian signature, there are 4 components of the Lorentz group. So let's call the identity component SO plus the D minus 1 comma 1.
Yeah.
Okay. Then there's another component, which is everything in the identity component times RT.
Yes.
So a priori, that doesn't have to be a symmetry just because the identity
I know that's the
component is.
X.
But if you look at a complex section of the group, then those two are actually both in the identity component.
Correct.
And that's kind of the proof, right?
I understand that, but what were you saying is the set in Euclidean space it's rotation by pi?
Oh, okay. Well, so in Euclidean signature, let's pick the x1 direction. Right? So this is an aside, and since we have time, I'll give the aside. So the best proof of the CRT theorem is that you look at some Euclidean correlator, and there's a symmetry of Euclidean correlator. I'm going to say I have 2 operators here, which is that I do a rotation by pi like this. And since that rotation is part of the Euclidean version of the lens group, it has to be a symmetry. But then if you take that statement about correlators and analytically continue back to Lorentzian signature, that operation switches the time order of these things, right? So if you ask what does this do, right, it inverts Euclidean time and it inverts this, right? So that's the R and the T. Then when you continue back to Lorentzian signature, you have to get an anti-unitary symmetry because it exchanges the order of the operators.
Okay, so it's fine that rotation enters into proof of CRT.
Yeah.
What you were saying in the statement of CRT had some.
No, I said
saying
for me the proof of the CRT theorem. So the definition. I mean, if you ask what is CRT,
it's right? Theorem in Lorentzian period.
Yes.
Okay.
But yeah, absolutely. Okay. But it's but you ask what is the like how do you define the CRT transformation in Lorentzian signature? So historically the definition was that it's the product of C, R, and T. But that's a terrible definition because those might not be symmetries, and even when they are, they're ambiguous. So my understanding of the statement of the CRT theorem is that the transformation which you get by doing a rotation by pi in Euclidean signature and analytically continuing is always a symmetry. So that's the definition of CRT. It doesn't require C, R, and T separately to make sense. Does that help?
Yeah, I agree with all that, except I mean rotation by pi in Euclidean was already came to an element in the identity.
No, I mean that's the fun thing, right? Is that in Euclidean signature there are only 2 components.
Yeah.
So RT, because RT in Euclidean signature is in the identity component, right? It's this rotation.
I think we're good.
Yeah. Yeah. That's why it has to be a symmetry. It's in Euclidean signature. It's in the identity component. Okay. Good.
By the way, just a comment. If you use CRT theorem, there's assumption about the Lorentzian invariant theory.
Yes.
Continuous component, but for quantum gravity, we believe this will still be.
Yes. So I think, as far as I can tell, quantum gravity has to be Lorentz invariant. Yeah, but we could have a whole discussion about that. About why?
Okay, so that'll be
but it seems, yeah, I mean, so there are things like loop quantum gravity that aren't Lorentz invariants, and I think they don't actually work.
What about this restrict gravity?
Yeah, I don't think that works either.
Okay, so you also put that up.
Yeah. Yeah, it's very hard to break Lorentz invariance in the UV and then restore it. What usually happens, because in renormalization group language, because they're marginal operators that violate Lorentz symmetry. So for example, if you have 2 different fields, then you could have one of them move at a different speed of light than the other. And that's a marginal operator because it just affects the kinetic term. So then that vanishes only logarithmically as you go to low energy. And logarithmically, we're actually not that far from the Planck scale. So if Lorentz symmetry is violated at the Planck scale, probably it generates operators like that, and then we should actually see them, but we don't. So that's some empirical argument. Okay. Right. So this was just some high level argument that, okay, and this I should put, parentheses, in quantum gravity. It doesn't make much sense to try to gauge space-time inversions if you're not doing gravity. If you're good, meaning that the identity component of the diff group should also be gauged, or the identity component of the Lorentz group, let's say. Because the things like R and T don't need the identity component. So to gauge them without gauging the identity component breaks the identity component. Okay. As we were just saying, it's bad to break the identity component. Okay. Fine. Similarly, so I phrase this in terms of CRT because I could say it's always a symmetry. But if you have a theory of quantum gravity where some other inversion, like say T by itself or R by itself, is a symmetry, then it also has to be gauged because it's also not allowed to be global. Okay, so we can consider theories where those are also separately gauged. That I just don't have an argument that they have to be there. Yeah.
Wait, that's a quick question. So I just wonder what do you mean by global symmetry in quantum gravity? So my understanding of global symmetry is that, for example, it is some operation generated by a line operator.
Yeah.
But so that requires locality, right? So then if you want to define that operator,
okay, so that's a long story. So when we write the proof that quantum gravity doesn't have global symmetries, right, we first have to say what it would mean for it to have a global symmetry, right? So in quantum gravity, indeed there aren't local operators, so you can't define a global symmetry. Say zero form symmetry is something that acts on local operators. You instead have to define it as a symmetry that acts on a local operator together with its gravitational dressing. So in my long paper with Agur, we have a whole section about that, explaining how to make the idea of global symmetry compatible with different variants.
But you also have to address that global symmetry generated.
That's correct. Yeah. Although in some sense it's not hard to address because it's a topological operator, so it kind of it can kind of be anywhere. I mean, you just have to know whether or not it's ahead or behind of the other operators that are around. So it's not too hard. It's a fairly discrete.
It is on the perturbative level. You do need a space on picture exists.
No, yeah, but I think so. I mean, from a perturbative level, you can certainly write down a Lagrangian,
right?
Which is Einstein gravity coupled, I don't know, to phi of 4 theory, which has phi goes to -phi as a global symmetry and navigation. You can certainly write it down. Then you can think about what does it really mean in different variant language, but the idea really makes sense.
Sure.
Yeah.
Why don't you consider gauging the entire line?
What?
Why don't you consider gauging the entire line?
Well, I'm going to because I'm doing gravity, so I'm indeed gauging. But I mean, when you say the Lorentz group, as Dan said, you have to be more precise because there's the biggest one has 4 components, and we can discuss which components are actually which ones are gauged.
This is building up.
Yeah. Well, yeah, but I mean, in gravity, I'm implicitly always gauging the identity component. So it's just the only non-trivial question is what do I do with R and T? Okay. So, all right, fine. On the other hand, if you think about this, if you say that CRT is a gauge symmetry, or more generally T, for example, is a gauge symmetry, you get yourself into confusing situations, right? So let me give you an example. So for simplicity, let's first just say that T is a gauge symmetry, right? What that means is that there are valid configurations of the universe where you go for a walk around a circle, and when you come back, the orientation of time was flipped. Okay. So let me give you an example of such a geometry. Just make space for it here. This is a 1 + 1 dimensional geometry of Lorentzian manifold. Okay, which we call the Lorentzian Mobius strip. Okay, so this is a perfectly valid Lorentzian manifold, right? I just take this piece of the blackboard with a Lorentz metric on it, with t going that way and x going that way, but then I just identify these two sides with opposite time orientation. And so if I say that time reversal is gauge symmetry, then one consequence of that would be saying that this is a valid configuration of the universe. Yeah,
So you don't require time orientation on your Lorentz manifold.
no. Yeah, so indeed, this is not time orientable.
Right.
And when you say that T is a gauge symmetry, what that means is that the transitions of functions are allowed to invert the direction of time. So then, indeed, so this means,
But in quantum field theory, you would require time orientation.
no, and that's what we're going to discuss. Okay. And so indeed, in the literature, as Dan maybe is referring to, there have been claims. So it's right. So I mean, so you know, like whenever you read a book about general relativity, right? There's the chapter on causal structure and so on. And the first sentence is that we're going to restrict to geometries that are time orientable because to not do so would be ridiculous. Okay, like if you go look in Wald or in Hawking and Ellis, there'll be a sentence like that somewhere. And I'm saying no. We're going to have to make sense of this. And then you could indeed ask, like, doesn't this have obvious causal pathologies, right? Does it even make sense to do quantum field theory on this geometry? And there have been arguments in the literature that doesn't, okay? And so now we have a real problem, right? We either have to decide that one of these two statements is wrong, or we have to say that we don't agree with the people who say that you can't do quantum field theory in geometries like that, and that's going to be the subject of this talk. All right, yes, more.
Well, I wouldn't say you need a time orientation because it's ridiculous otherwise. I mean, even in Minkowski space-time,
Yeah.
as I understand that the role of the time orientation is really that gives you a notion of positive energy. Without having a notion of positive energy.
So I mean here, like, since I'm doing gravity, the Hamiltonian is zero anyway, right? I'm going to close the
Well, I
universe.
said in quantum.
Yeah, so I think, as I was saying, we're only going to want to do this in quantum gravity.
Well, that's why I asked in quantum field.
No, but I think even in quantum field theory, it's okay. It's just that, so let me say it in a different way, right? So you can certainly do quantum field theory in a time-dependent background, like de Sitter space. And that doesn't have time translation symmetry in the first place. So you wouldn't talk about the energy. And similarly here, this just doesn't have time translation symmetry. Yeah, I'll say a lot more about quantum field theory and this geometry a little bit later, and then we can complain more if we want to. That's not the criticism that was usually given. The criticism that was usually given of this is that in order to quantize this, you might want to impose some canonical commutation relations, say on the t=0 slice. But then you can say there's a dot here. And so which direction does that dot go in? So that's one. There are two traditional criticisms. This is one of them. I'll say the other one when I get to it. Okay. But I don't think this is a serious criticism. All right. So actually that was all I was going to say for the introduction. Now we're gonna try to get into it and see if we can make sense of this. There's things in the chat. I don't know if they're questions. No, okay. All right. Okay, so let me go on. So I want to first do a review of something which I guess many people here are comfortable with, but I'll do it anyway. Which is what it means to gauge a discrete internal symmetry. Okay. So this is a standard topic depending who you talk to. If you talk to a phenomenologist, they don't even know what the words mean. But you know, if you talk to people probably in this room, they know, but let me try to say it in my language. This will be a warm-up, so then we can go think about how to do discrete space-time inversions a little bit later. Let's start with a theory with a discrete internal global symmetry and turn on a background gauge field before, right? So when you gauge, kind of two steps. First, you turn on a background gauge field, and then to make it dynamical, you sum over background gauge fields. Okay. So let's do the two-step process. Let's first just think about what it means to turn on a background. Okay, so mathematically, so let's say we're in a space-time M, okay, with a global symmetry group G. It's a zero-form global symmetry. I'm not going to do higher form symmetries in this talk. These space-time symmetries are zero-form symmetries. There's no reason to go to higher forms. So I'll first say what almost is the definition of a background gauge field, and then there's an asterisk to fix it. So the thing that's almost the definition is it's a homomorphism from the fundamental group of M to G. And the idea of this is that this is in the discrete case. Of course, the general definition is it's a connection on a principal G bundle. Okay, but for the discrete case, it reduces to what I'm going to say now. So the idea is for each closed loop in M, I have to tell you what's the holonomy if I drag a charged object around the loop. Okay, and the holonomy is given by this homomorphism. And it has to be a homomorphism because if I go around this loop and then I go around that loop, I should just multiply the holonomies. Okay. Now, that definition is actually not quite correct. The reason is because the holonomy is not gauge invariant. So usually when you define a Wilson loop, you have to do the trace, right, to get something gauge invariant. That's because the holonomy transforms by conjugation under gauge transformations, which means that I should identify homomorphisms which differ by conjugation by an element of G. Okay, and so that's the definition of a background gauge field. It's the set of it's a homomorphism modulo this conjugation by an element of G. Now, that's correct, but somewhat formal. So let me try to say in practice, okay, I give you a quantum field theory with a global symmetry. How do I compute things in the present, with one of these background fields turned on? Okay. So the idea, so let's say that I want to turn on a holonomy around this loop, right? So what you're supposed to do, so since it's a quantum field theory with a global symmetry, there's going to be a unitary operator U of G, which is codimension 1, which is just the operator that implements the symmetry on the Hilbert space, right? In quantum mechanics, at least for internal symmetries, they're always represented by unitary operators on the Hilbert space. Okay? And so the idea is I take the one cycle around which I want to have a holonomy, and then on the Poincare dual cycle, or more accurately on a Poincare dual cycle, I wrap U of G. And the reason that turns on a holonomy is because if I put an operator O here that's charged under the symmetry, and I pull it around the loop, then at some point it gets stuck on the symmetry operator. Right? So if I pull it around, at some point I have to do something like this. And then if I keep going further, then what I should really do is just break off a piece of the symmetry operator. And then now I can just drag this gadget around the rest of the way to here. But this, of course, is just the symmetry. This just gives you the symmetry action on the operator, right? So then you see that SO goes around. When I get back to here, you could call this like D of G times O. So that implements the holonomy. Right? And so to turn on a general background, you have to turn on a network of these operators sort of wrapping one on the dual cycle for each of the loops. Okay.
So there's no distinction between space and time here, it's not necessary.
Yeah, this could be either Euclidean or Lorentzian, I'm saying now.
Yeah, okay, so I shouldn't think of the U of G is not a thing you put on time slice.
Well, you could, but you can either put it on a time slice or a spatial slice. So it depends. So if this holonomy is spatial, right, then U is going to have one direction will be time that it's wrapped on. Yeah. But if you're, for example, in Euclidean signature and the cycle is the time cycle, then you will be space. Like I'll do an example in a sec where we're going to see that.
So this one is thinking deep. I thought that if something is moving in time, then it's a defect.
Yeah. So there's this terminology is terrible, and the practitioners in the field make it worse. Okay, so I think the best language to talk about this is that an operator is what von Neumann told us is an operator, which is a linear map on a Hilbert space. Okay, so that's always an operator that's mapped in the space direction, that's wrapped in the space direction. If you have something that's extended in time, it should be called defect because it's changing the Hilbert space. Okay, and if you want to talk about them both using the same word, call them insertions. Okay, I think that's the correct language. You know, some people haven't figured this out yet and use the word operator where they shouldn't, but I think von Neumann defined operator and we should stick to von Neumann. Well, probably he didn't define it, but yeah, I'm sure that idea goes back further than that, but he was really good at them. Okay, so let me do an example of this just to make it a little more concrete. Okay, so that's turning on the background. Now let's sum over backgrounds. So in principle, we just sum over these networks of defects, but let's do an example so it's more concrete. So let's do an example where M is a torus, 2 torus, and G is Z2. So now this is Euclidean because I made the spacetime torus. So then here's what it looks like. So now to gauge, we should sum, right? So here's what the gauged partition function looks like. So more accurately, you should divide by the volume of the group in sum. Okay, so here the volume is 2. And then there are 4 terms. Okay, there's a term with no holonomies of any kind. That's the easy one. Okay. Now let's be clear. There's a term with a holonomy in the time direction. So then what I'm drawing here is U of G. Okay. So this is a term with holonomy in the time direction, but not the space direction. There's a term with holonomy in the space direction, but not the time direction. And then finally, there's a term with holonomy in both. Okay. Now let me just make a comment about this term because someone is probably wondering. So you see here the defect operators are intersecting with each other. And in principle, you could worry that there's some UV issue with defining the intersection where you require more data here than just saying it's these two. If that's true, if there are different choices here, then you say that the Z2 symmetry has an anomaly and you can't gauge it. Okay, so that's the discrete version of the idea that anomalies come from contact terms in currents in quantum field theory. So in this talk, I'm gonna assume there's not an anomaly. If there's an anomaly, then obviously you can't gauge these things. Okay, so this is kind of, if you like, the path integral description of gauging. Now it's going to be useful for us to also have a Hilbert space language. So let me say that. So these two terms give a projection onto singlets in the ungauged theory. So if you have a Z2 symmetry, right, then the operator 1 plus U over 2 is a projection onto the states of charge 1, right? Because if a state has charge 1, I get 1 plus 1 over 2, which is 1. And if I have a state of charge minus 1, then I get 0. Okay. So this is just inserting from the Hilbert space point of view this projection onto singlets into the Hilbert space that we started with. This term is again a projection onto singlets. But not in the original Hilbert space, and instead in a new Hilbert space, which is conventionally called the twisted sector. Okay, so this is the Hilbert space you get by cutting this way. So then there's some operator here where the fields jump across this operator in some way, right? And that defines a new Hilbert space. So maybe just to mention two examples of this. Oh, you have a question?
Yes. So just make sure when you say that the Z2 symmetry cannot be gauged if there is an anomaly.
Yeah.
And
Yes.
As the usual case in quantum field theory, that happens. That if there's 1 plus 1D theory, maybe a CFT with a Z2 symmetry, or maybe just the usual any 1 plus 1D quantum field theory with Z2 anomaly, it's possible you can aid a 2 plus 1D bulk invertible field theory, such that you can gauge this 1 plus 1D theory and 2 plus 1D together. So that's the case for quantum field theory.
No, I think that's, sorry, I mean, yeah, so people sometimes say these things. I mean, I gave a talk about this at some point. The definition of an anomaly is not something that comes from a topological theory in 1 dimension higher. That's something that seems to be true for the anomalies that we know about, but I view it as an open problem whether all anomalies can be interpreted that way. The definition of an anomaly is that it's an obstruction to gauging the symmetry. And so the way to see it explicitly here, the only thing that could fail here is if there's some problem defining this so that I can't interpret the sum of these two terms as a projection onto singlets in the twisted sector. And the way it can fail is if there's different ways of resolving this, depending which way you look at it. So there's a nice paper by Xu Hang and I think yeah, which explains that.
But my point is exactly that, is that there's a minus sign maybe regarding the last terms on it, right?
Yeah.
So that's basically capture this anomaly by a 3 cycle in terms of this term. And in the usual quantum field theory or condensed matter system, you can resolve that by adding the 2 plus 1D.
Yeah, in this example you can, but I don't think that should be, I really don't think that should be the definition of an anomaly.
Okay.
That's true
then
for this example, but that doesn't mean it's true in all examples, and there's no proof that it is.
Okay.
Yeah.
Yeah, my point is that maybe you are consider quantum gravity so that even if the system let me have any notion of CRT anomaly of total anomaly with that symmetry, then maybe that's not a whole system at all. You should also consider some additional systems such the whole CRT does not have anomaly. That's why you can gauge. I guess.
I mean, you can try. I think it's better to just say you shouldn't gauge it. If you add something else to the theory, it's a different theory, and now we can study that theory, but that's not the theory I'm interested in. Yeah. Okay. Yeah, so I was going to mention two examples of this. Yeah, sorry, go ahead.
Is this twisted sector a subset of the original
No.
Hilbert space?
No, it's a new Hilbert space. So yeah, so for example, if we could do a free scalar, and the symmetry could be phi goes to minus phi symmetry. That was the first example I was going to talk about. So that's the Z2 orbifold from string theory. So people from string theory know it very well. Okay. And then in the untwisted sector, phi is periodic as you go around the circle. And in the twisted sector, it's anti-periodic as you go around. So there aren't anti-periodic states in this Hilbert space. It's really a new Hilbert space.
Yeah, so I need both of the four by configuration for any not just if I want to gauge this.
Yeah, nothing I'm saying involves conformal symmetry here.
But I can understand these last two configurations if the theory is because I have modular theory. If you are referring to force.
Sorry, I don't understand. You have what?
You have modular theory on force, for example. So
I don't know what that means.
Modular.
Oh, modular invariance.
Yes.
Yeah, I see. Sorry, but you're
Yeah, so for that, I can understand why I have to include these last two configurations. But let's say for a non-CFT, for example, 2D non-CFT. So how
no, okay. You guys keep bringing up all these pet peeves of mine. Okay, so modular invariance is not a principle of quantum field theory. The principle of quantum field theory is locality. Modular invariance is a consequence of locality. Okay, it's not the only consequence, you know. So in CFT language, it turns out that you can take locality, which is a very general principle, and turn it into, you sort of replace it by crossing symmetry and modular invariance in 1 plus 1 CFT. But that's just some accident of 1 plus 1 CFT. It's not CFT. It's not true in higher dimensions or even in non-conformal theories in 1 plus 1 dimensions. So here I'm not trying to use conformal symmetry, right? It's just I'm trying to say what the general rule is for gauging. So I think this interpretation is always correct. And you always have to include all these terms because you want to have the definition of gauging be that you sum over background gauge fields. And so if you forget to include some of the background gauge fields, then it's a violation of locality, right? You're not summing over all the possible backgrounds. You're putting some weird constraint on the fields that you're summing over. You know, it would be like saying, I'm only going to sum over, like if I tried to do the scalar path integral over a free scalar, but I said, no, I'm only going to sum over fields where if I integrate phi along a spatial slice, I get 10. But why would you do that, right? Like that's a very non-local thing to do. It's going to destroy the axioms of quantum field theory.
Well, maybe this is 9 plus. So my understanding of the first inverse is that, so I'm constraining my Hilbert space.
Yeah.
To only contain the states which are invariant under this.
Yeah.
So I think in this sense, I can understand that I'm gauging this. But the other part why I actually include additional sectors in my Hilbert.
No, because a gauge symmetry is supposed to be a redundancy of description, right?
Right.
So if I go around a circle and come back to where I started, if this Z2 is a redundancy of description, then I had better allow configurations where that redundancy happened, right? I think you can just think about it like that. It's like when you're defining a connection on a bundle or something, right? Like you want the rules for computing the partition function to be local. You know, so it's a redundancy, it's a local redundancy. There can't be some weird global restriction on it. Yeah, so somehow a failure of modularity is really a failure of locality, like that. Yeah. Okay. So actually, oh, yeah, I was just going to mention maybe in passing. So I said one of the examples already. That's the Z2 overfold. Another example is in the Ising model. So if you do the 2D Ising model, so what I was told in kindergarten is that at the critical point, the 2D Ising model is equal to a free Majorana fermion. Okay, this is not correct. Okay, if you learn one thing from this talk that you did, probably you know this, but if you didn't know this, learn it now. Okay, it's not correct that a free Majorana fermion is the critical Ising model. Okay, to get to because the critical Ising model is bosonic. There are no fermions, right? There are no operators with non-zero fermion number. Okay. So the critical point of the Ising model is a free Majorana fermion with fermion parity treated as a gauge symmetry. So any operator which is a fermion, like from Jordan-Wigner, whatever, has a line attached to it, as you know from Jordan-Wigner, and that line is the Wilson line of the fermion parity. Okay. So the Ising model is another example of this. Okay, so that's all I was going to say for the internal case. Now let's go on to time reversal. Subir can hear 10 minutes. Unfortunately, it means you hear the formalism part of the talk and not the fun results that come from the formalism. So let's try to now apply what we learned to time reversal. Okay, I could also discuss spatial reflection R. There's an interesting story, which is that the twisted states of gauging spatial reflection are open strings. Okay, which is a somewhat controversial topic in the history of the subject, but it's true. Okay, so in Joe's book, for example, he says it's not true, but nonetheless it's true. So if you want to hear about that, ask me later. I guess most of you aren't string theorists, so you don't care about the unoriented string. So let's go on to time reversal. So we're exactly going to study this free scalar on this Lorentzian Mobius strip. Okay, so the boundary condition. So I'll take this to have length L. So there's a boundary condition which says that if I go distance L in space, then I get back to where I started, but with the direction of time reversed. Okay, and so now in this language that we introduced, the idea is that this theory is the twisted sector of gauging time reversal. Okay, and then eventually we're going to want to project on the singlets, right? Because we're really supposed to. So this picture I'm drawing, it's like sort of this. It's quantum field theory in this background. Okay. And then we're eventually going to want to sum over these two and project onto singlets. But the tricky thing, I think, is just defining the twisted sector in the first place. And so that's what this theory is going to be. And so I want to emphasize, so I said that in order to actually gauge time reversal, we probably want to be doing quantum gravity. Okay, I think that's true. But to turn on a background field for time reversal, we can just do that in quantum field theory. Okay, so that's what I'm going to be doing here. Okay, the first thing I want to say about this is that if you look at t equals 0, this theory has a fairly reasonable set of initial data. Okay, so if we just think about it classically, right? What did these equations tell us classically about the initial data here, right? It says that phi, so f t equals 0, phi has to be periodic, right? So if I put t equals 0 here, it just says phi is periodic. But then if I take the time derivative, then I get something anti-periodic. Okay, so if you like, that's kind of the definition of the twisted sector, is I take, wave functionals of phi here, but with the rule that phi is periodic and phi dot is anti-periodic. Now, this is a fairly robust set of initial data, right? You can vary things independently in different places. Maybe I won't inflict it on you, but you can write down a complete set of solutions of the wave equation for arbitrary initial data here. So you just have to figure out what the modes are that obey these boundary conditions. So at the level of solving the classical equations of motion, it seems there's at least a candidate nice phase space, which is just the set of all solutions to the wave equation, obeying these initial conditions. And you can check that indeed the solutions obey this everywhere and not just at t equals 0. So that's good. On the other hand, you have to deal with this issue with the canonical commutation relation, which I erased, so I'm going to write it again. Okay, you have to say, what do you do about the time derivative here? Now, actually, I want to emphasize something over here before I go back to that. So I gave you a definition of what I mean by a background gauge field. But if you look at what I did here, right, the correlators in this background actually depend on more than just W, because they depend on the location of this brane. Because if I move, this location is the place where O picks up the transformation. And now you can try, so essentially, if you like, there's some sort of branch cut in the correlation functions. And to really define them as functions, you have to say where the branch cut is, okay? You can try to define them as sections of something, right? And then you don't have to talk about that. But if you really want to define them as functions on the space where you started, then you're going to have to tolerate a discontinuity here, okay? And so my claim is that the same thing is true here. We have to pick, in the sense of if we want to define things as functions, we have to pick a location of the time reversal operator, which is extended in time. And that will be a point across which our definition of the time period here changes. Okay. So in other words, so the easiest thing to do is to pick it to be here, okay? And then I just say, time is going this way here, and I just tolerate that things are going to be discontinuous as I go across. Now, as in this case, once you actually gauge the symmetry, this extra information goes away. Because in order to find the location of this thing, you need to move a charged operator across it. And once you gauge the symmetry, you get rid of all the charged operators, okay? So this partition function, I can really view as just a sum over these W's, because even if I wanted to sum over the location of the branes, it wouldn't do anything, okay? And so I claim the same is true here, and that's why this is, the fact that there's a discontinuity here is not so bad. The only thing you really need is that the discontinuity matches on the two sides. Now you might say, well, this doesn't look very discontinuous, but you have to remember that there's an I here, and that time reversal is an antilinear operator. And so when you move across it, I does change sign. Okay, so both sides of this change sign as you move across, and so it's consistent to just pick a direction of time here and impose it here, and then just accept that there's going to be a discontinuity at the edge. Right. Yeah.
The discontinuity is as you go around the spatial slice.
Sorry, what?
The discontinuity is
Yes.
in the spatial slice. or-
Yes. Yeah, and the same was true here, right? So if we think of this as space and this is time, because we're in the twisted sector. Yeah.
Yeah, so, if phi dot, so I mean, so from the game theory perspective,
Yeah.
phi dot is not, it's not an operator.
Yeah, that's right. So that's why it's okay, right? So that's why you can't detect the discontinuity once you go to the gauge theory.
Starting from this canonical theory.
Sorry, what?
You define your quantum theory from canonical.
Yeah, but right now what I'm defining the quantum field theory in the presence of a background field. I haven't yet gauged the symmetry. So in the twisted sector, phi dot is a fine operator.
Oh, okay.
It gets killed when I do the projection here, but I haven't yet done the projection.
But after the gauging, so-called everything.
No, but after the gauging, then it's fine, right? Because the discontinuity is gone. Because you only get to talk about T invariant things. So if I, for example, if I put phi squared here, I wouldn't have any problem, right?
Can be modified.
Yeah. Yeah, I mean, it's the same as for the internal case. I mean, everything that happened in the internal case happens here, but it's not worse, I don't think. Yeah, I think so. So I think in the literature, people were confused because they wanted to define this. For example, this choice breaks the symmetry of rotations as you go around here, which is a symmetry of this purely as a geometry. And so you can complain about that, and they did complain about it. That was why they said this shouldn't be allowed, is because they wanted to quantize it in a way that preserved the rotational symmetry. But I think it was just a mistake. If you think of it as a background for T symmetry, then you shouldn't have that symmetry until you gauge. And when you gauge, you do. And that's good enough for me. Okay. So that was subtlety number one in the old literature, which I think is fine. There's a second subtlety, which is that there are no natural states. Okay. So let me try to say that. So in quantum field theory, right? I mean, so to be clear, this has a Hilbert space with positive norms. So it's not that there aren't any states. The problem is that there's no particularly nice states. And it's similar to doing quantum field theory in a time-dependent background, right? So if I just, I do quantum field theory in Minkowski space, but then I put some bumps in the metric here and there to break time translation symmetry, then there's no ground state, right? So that's our favorite special state. Now, what we do in the context, say, of de Sitter is that we use Euclidean path integral to prepare a state. So you can do that even if there's not time translation symmetry, and also for the black hole, right? We can talk about the Harlow-Hawking state. Here, it's even worse. So let's try to use the Euclidean path integral to define a state and see what we get. Right? So if I want to do that, so say I want to define some state that I'll call rho hat. So the natural thing to do is to take the Euclidean Mobius strip and then kind of put a phi initial boundary condition here, a phi final boundary condition there, and do the path integral. So how shall I say? So now you see I put a density operator here, not a pure state, right? The reason I had to do that is because these boundary conditions could act the bra and the cat. So at best, I'm going to get a mixed state. I'm certainly not going to get a pure quantum state out of trying to use the Euclidean Mobius strip. So I can certainly define an operator rho hat this way, right? This defines an operator. But in order for this to be a state, rho hat has to be a positive operator. And if you just look at this, why should it be positive? There's no reason for this path integral to be positive. And in fact, it isn't. Okay, so rho hat is not positive. Or even Hermitian. So this is a thing you can define, but it's not a state. So then you have kind of a problem, I mean, it's not a serious problem because the theory is fine. There's a Hilbert space. There's self-adjoint operators on the Hilbert space. You can compute expectation values of the operators in the states. But what are you going to compute, right? You know, which state do you pick? Which operator do you pick, right? It's not clear that there's anything interesting to compute in this theory. Yeah. What? What is the Hilbert space? Yeah. So I think I think a way you can think about it is you take functionals phi of x that are periodic, functions of phi of x that are periodic, but then you restrict to wave functions where minus I dd phi is antiperiodic. Because you want to replace this. So I can just formally define a Hilbert space like that. Now, strictly speaking, I should have two normalizable states and so on.
Sorry, now I don't quite understand the arrows in that picture of a path integral. You're not gluing the top right to the bottom left, right? Just the way you.
No, I am. Yeah, this is so there's a boundary condition that this is identified with that. And similarly, this is identified with that, right? So that's why it's not a pure state. If these things weren't connected, it would just be the outer product of the pure state itself, right? But then if you like, the pure state comes with a label, which is the boundary conditions here, and then I have to sum over those labels, so that makes it a mixed state.
And why are you making that identification? It's
because I want to get something that acts on this Hilbert space, so it has to respect this anti-periodic nature of phi. So actually, I'm going to give this a name. I'm going to call it the Mobius. I should write like that. Pseudo-state. Yeah.
Sorry, I think I agree with that. With this specific basis, rho can be written as a matrix. But like it's not clear to me like whether rho is an operator or not, in the sense that if you have a symmetrical operating on this Hilbert space, like does rho really transform under unitary representation of?
Well, no, I just to define an operator, I just have to define it in a basis, right? So I'm just defining it in a basis here. That's it. I'm going to give you in 2D CFT, I can give you a formula for rho hat, which I'm going to give you in a sec, which I think will make it more intuitive. But yeah, I mean, to define an operator, I just have to tell you how it acts on the basis. Wouldn't you say? Well, in principle, we can worry about the domain of the operator and so on. Probably we should if we're being careful.
Sure.
Yeah.
Maybe that's possible.
Yeah. Okay. So I want to make this more intuitive. And I promise things are going to get very concrete in a minute. We're almost done with the formal part of the talk, but we have to go through this to just get all the language in place. I can compute this rho hat explicitly in 2D CFT. So the idea is I take this picture. Okay, and then I take the top half and I just kind of plop it over like this. Okay, so I'm going to rewrite the top half down here. But since I plopped it over, something nice happens. And then here I get time reversal acting on phi initial. Okay, because I plopped it over. But you see, now this is something very civilized, right? You see, now these identifications are going the same way. These identifications are going the same way. So this thing is preparing the ground state of the theory on a cylinder that's twice as big with the usual boundary conditions, cylinder boundary conditions. Okay, so this thing is equal to the wave function of the theory on the cylinder of radius 2L, but with this funny time reversal thrown in here. Okay, so that's true in general, actually. I didn't yet use conformal symmetry. The place where I can use conformal symmetry is that in conformal field theory, I know the wave functional on a cylinder because I can map it to the infinite space, and then I can use the Rindler decomposition. Okay. So I won't sorry, go through the details of that. But what this tells you is that in 2D CFT, this rho hat has a nice formula. It's e to the minus pi k L, where this k is the modular Hamiltonian of half the cylinder that's twice as big. Okay. And then times a product of two anti-unitary operators. So CRT, which as we've discussed is always a symmetry, and then theta t for time reversal. So of course, we're assuming time reversal is a symmetry here, or we wouldn't even be having this discussion, okay? So put this here, okay. And so what you can see is that the Mobius pseudostate is a positive operator times a unitary, because the product of two anti-unitaries is unitary. And so in particular, it's not positive, right? It's not Hermitian, right? But it's a positive operator times a unitary. Now, I think I won't go through it because the details are somewhat boring. But if you want something to compute in this theory, the nicest thing we could think of is to just compute correlation functions in the Mobius pseudostate. So I would call these computables and not observables because it's not a state. But there's something nice to compute, and you can use them to characterize, the causal structure of the theory. You can check that the correlators are consistent with the choice we made for the canonical commutation relations. I think I won't drag you through that. I'll just say that once you have this, there's a set of things. All right, so far this has been somewhat dry and technical, so now I want to actually have fun. Okay, I'll tell you some things about quantum gravity that we learned from this. But I'm happy if there are more questions, concerns, complaints. Yes?
Is there a relation between the pseudostates and the states of the theory?
Not obviously, right? You can check if you chase through these things here, you can sort of check that this thing has the right boundary conditions to be consistent with the anti-commutativity. So the anti-periodicity of phi dot. No, but I think, the thing is you just have to accept that there's no natural state. It's like quantum mechanics with the time-dependent Hamilton. Just what are you going to do? Somehow you have to have a physics problem in mind to decide, what states are interesting. But just to characterize the theory, I can compute things like traits of rho hat, O of x, O of y. And they aren't physical correlators, but they're computables that you can use to study the theory. And so we did a fair bit of that in the paper. And I'll actually, I'm going to do ADS CFT in a second, and I'll mention that one of these does end up being interesting. Okay. Maybe I should just say as a historical comment. So there's a long history in Euclidean signature of turning on backgrounds for R, right? That's the business of taking a Euclidean field theory and studying it on a manifold that's not orientable. So that goes back to the 80s. The new thing here is to go to Lorentzian signature, and then you have to deal with the fact that R and T are different. And so you get different things depending which one you gauge. And that was somehow hidden by just working in Euclidean signature, which is what people always did in the past.
So you're saying hidden, but it's already contained, like when we do some of the topologies, patterns.
Yeah, but it's complicated because in Euclidean signature, CRT is always gauged because it's in the identity component. And so if you're doing gravity, then it's going to be gauged. So then it's hard, there's not really a difference between gauging R and gauging T, but really CT. You kind of, either you gauge both or you gauge neither, and that's this choice of including unoriented geometries or not. In Lorentzian signature, you have this additional choice, at least from the low energy point of view, which is to not gauge CRT. That's not a choice you had in Euclidean signature, but it's a choice you have in Lorentzian signature. Now I'm actually saying it's wrong, right? I'm saying CRT has to be gauged, but you can't see it just by looking at low energy path integrals.
But I'm trying to understand that you're trying to make sense of this sum of topology that includes unoriented manifolds in Lorentzian signature. The Euclidean pathway is not missing this gauging.
Right. But I mean, the thing is, so Euclidean gravity is very confusing, right? Because it's not equal, you know, in quantum field theory, you know, the relation between Euclidean and Lorentzian is simple. You know, there's analytic continuation, you can interpret things in the Hilbert space formalism. But the usual calculations of quantum gravity in Euclidean signature don't have Lorentzian interpretations within the Lorentzian theory. They're sort of inequivalent starting points for trying to quantize the theory. And so there's a lot of fight in the literature about you include this geometry, you don't include them. So for example, in 1+1, right, with JT, right, if you do the Euclidean quantization, you don't get quantum mechanics at all. You get like this average over quantum systems, right, which is not quantum mechanics. If you start from Euclidean point of view. If you start from the Lorentzian point of view and do canonical quantization, you're of course going to get quantum mechanics. So they're just different. Yeah.
When you use manifolds, Lorentz manifolds that are not time-orientable, there's a double cover.
Yes.
And are you building in that flipping the sheets is complex conjugation?
Yeah, that has to do with whether you gauge T or CT. So that's a choice you can make. Yeah, and in fact, strictly speaking, so I buried this distinction by doing a real scalar field here because I didn't want to have the discussion. But if you do a complex scalar, then if you gauge T in Lorentzian signature, then in Euclidean signature, when you go around, it should really be CT, and vice versa. So if in Euclidean signature you say it's a time reversal as you go around, then when you go back to Lorentzian signature, it's CT that you gauge. So it's a choice, you can do either. If you have both symmetries, you can do either. Yeah.
Shall I worry that KL?
Sorry, say it again.
Shall I worry that KL, the KL operator, is not a well-defined operator?
Good. So yeah, you can worry about it to the extent that you ever worry about this kind of thing. Yeah. Yeah. You know, I'm not a mathematician, so it's okay for me. Yeah, you know, it's the usual. I think the right way to say it is it will have some very restricted domain, but as long as you only use it to compute the things you're supposed to compute, then it's fine. Yeah. And certainly if you have a regulator, then it's totally fine.
Right.
Yeah.
So the original Hilbert space becomes a subregion Hilbert space after it
It becomes what?
a subregion Hilbert space after.
Yeah, that's right. But that's just I'm just computing this function now. I'm not actually computing anything in this Hilbert space because remember this operator just acts here. Right. So I'm never actually computing anything on this whole Hilbert space. I'm just using it to get a formula for this. So, but I can do everything just in terms of this without needing the bigger Hilbert space.
Just make sure one terminology. You say rho is not positive, but earlier, very earlier.
Yeah.
What do you mean? You mean the eigenvalue is not positive?
Well, okay, so yeah, so in finite, so you have to be careful about that because it's not Hermitian, right? So yeah, so I mean a positive operator will be Hermitian, I guess. So then yeah, I mean one definition of positive, I guess, is it's a Hermitian operator whose eigenvalues are positive. I think in infinite dimensions we have to be a little more careful. I think what I would mean is that for any state psi, and actually for a state I should probably put no, I should put that. Yeah. Yeah, that to me that's the definition of a positive operator, is that for any state this is true. And so that should be true for a state, but it's not true here, certainly. It's this unitary here. Okay. All right. Now let's try to have some fun. Okay. I feel like this is too much formalism. So let's do ADS CFT. And actually I'm going to do ADS3 CFT2. So let me first remind you of some standard thing in ADS3, which is the BTZ black hole. Okay. So the BTZ black hole is the ADS3 version of the Schwarzschild geometry. So in Lorentzian signature, it has a Penrose diagram like this, where there are some singularity here, which is really in BTZ case a conical singularity. And then there are two asymptotic ADS boundaries. I will think about this in Kruskal coordinates, capital T and capital X, which cover the whole geometry, or T goes up. And usually what we do is we cut this at capital T equals 0, and we study it in the Harlow state. That's the thing we like to do with this geometry. There's also the Euclidean version. Okay. So here, by the way, it's this times a circle. There's a circle sitting on top of this that's trivially fibered. It's sitting over this because it's a three-dimensional geometry. Similarly here, in Euclidean signature, it's a disk with a circle sitting on top of it. And the idea is that you have periodicity beta as you go around, and you interpret this as computing the thermal partition function of the dual CFT2 on quantized on a circle. And in particular, when you do this calculation, you compute the partition function, C of beta, which in the semi-classical approximation is pi squared over 2g beta. Or if you want to write it in CFT language, it's pi squared c over 3 beta, where c is the central charge. So this is like, anyone who studies ADS3 gravity, this is kind of the first calculation that you do to figure out what's going on. So far that's standard. Now I'm going to take this and I'm going to do something bad. So I'm going to introduce a geometry that I call the CRT twisted black hole. So the idea is that there's I'll start in Lorentzian signature. So there's a natural involution of this geometry, like a Z2 isometry. So, and I can quotient by that. So let me say what the quotient that I do is. So I take T, X, and phi, where phi is the angle around the circle that's living on top of everything. And I identify this with minus T and minus X. So that's a CRT transformation, hence CRT twisted. And then, but okay, this would have fixed points if I don't do anything to phi. So then I'm going to shift phi by pi. Okay, it has to be pi because I want a Z2. Okay. So if I do this transformation twice, I get back to where I started, right? Because this is a shift by 2 pi. Okay. And this identification has no fixed points. So this is a smooth Lorentzian geometry. Let me try to draw what it looks like, right? So this reflection of X exchanges the two halves of this. So I can try to make a representation of this. Special surface here. And then there's one ADS boundary here, which is just the usual Lorentzian cylinder. There's a horizon like this, but then there's this funny thing where, if I fall in like that, then I come out down here going backwards in time and on the other side of the circle that I didn't draw. Okay. You can also draw it. I can give a more accurate representation by saying that, so this now includes the circle. The geometry consists of the region in between these two cylinders, where the outer cylinder is the ADS boundary, right, the Lorentzian cylinder. But then at the inner cylinder, I do some sort of antipodal identification, both in space and time. So this again is not a time-orientable geometry. In fact, if you look at the metric, in the topology just of this surface, it's our Lorentzian Mobius strip again. Okay, if you take the Lorentzian cylinder, that's this double cover Dan was mentioning. It's this, right? Then I do this identification, and that gives me the Lorentzian Mobius strip. So this is not time-orientable. On the other hand, from the boundary point of view, it's like totally kosher, right? This is just, it obeys the same boundary conditions that we think you should obey for the conventional CFT on the cylinder. So if the rule of ADS CFT is sum over all bulk geometries that are consistent with the boundary conditions, then at least if CRT is a gauge symmetry, then you had better be including this one too. Okay. Now, you might say, well, that's silly, Daniel. But what I'm now going to explain to you is that there's a calculation I can do in the dual CFT where this is the dominant configuration. And so to match the CFT, I have to include this. Okay, and so in some sense, this is a proof that in quantum gravity, we're going to have to learn to live with these things. Okay. So to do I first have to motivate the calculation. So by thinking about what kind of state I might like for fields in this geometry. Okay. Now S here, right, I'm going to run into this issue of no natural state. So I can try to define a Euclidean pseudostate. That would come from doing this same identification, but now to the Euclidean version of the black hole. So I can define again a pseudostate by final rho hat by initial. By taking the, let me draw it a little bigger, the Euclidean geometry with this identification. So then there's some, like this is somehow identified with that, but with including the rotation by pi. And then I put phi initial here and phi final there. Okay, so that defines a pseudostate from the bulk point of view. Here it's actually easy to see what it is from the boundary point of view as well. So from the boundary point of view, what is this, right? The idea is I start here at the initial state. So remember, it was beta to go all the way around. Right? So here I go a quarter of the way around. Okay, so I get e to the minus beta over 4 h. Okay. Then this is identified with that, but with a rotation by pi along the spatial circle. So I should put e to the I pi j here. And then I should keep going here. And then I just do another rotation, another evolution by e to the minus beta h over 4 to get back up to here. And then now that's the final state. Okay, so this is the CFT formula for the pseudostate. And of course, since j and h are commuting, I can rewrite this as e to the minus beta over 2h times e to the I pi j. Okay, and so look here we have again a positive operator times a unitary. All right, so it's the same kind of thing that we had over here. But from the CFT point of view, okay, fine, this is the thing. Now what I want to do is I want to compute. The easiest thing to compute is just the sort of, I don't want to call it the norm, but the trace of the pseudostate. Okay. So from the CFT point of view, that's trace of e to the minus beta over 2h times e to the I pi j. Okay. We can also insert correlators into this, and I'll discuss that in a sec, but let's just first compute this. Okay. So the bulk calculation is easy. Okay. Because I'm just supposed to compute the Euclidean action of this, which is just half the action of that, because I just did a Z2 quotient. So I should take this result and I should just divide by 2 in the exponent at the beginning order. So then I get e to the pi squared c over 6 beta. Okay, great. Now the CFT calculation. All right. So if you stare at this, right, this is computing the CFT partition function on a torus which is tilted by pi. Okay, so yeah, roughly speaking, something like this, right, where this distance is pi, this distance is beta over 2. Okay, so if you say that in terms of the complex structure parameter of the torus, there's a 1/2, which is real, plus, I always forget the normalizations of this. Yeah, good. And then there's an imaginary part, which is beta over 4. Okay, see you. So I'm just trying to compute the CFT partition function on this torus. Let's take this quantity and define it to be epsilon, because I'm interested in the limit where beta is small, because I want to do high temperature. That's where this should be like a black hole. If beta is large, I'm at low temperature, and this geometry probably won't be the dominant thing. It'll be I'll be computing something near the vacuum. Okay. Now, this CFT partition function is something that I can compute in any CFT by using cardiology. Okay. So let's see how it works. So I want to compute z of 1/2 plus I epsilon. All right. So I can first do an S transformation to turn this into minus 1/1/2 plus I epsilon. Then I can Taylor expand, since epsilon is small, to write this as z of -2 plus 4 times I epsilon. Then I can do a T transformation to get rid of the two -2's. Okay. And then now finally I can do S again. So this is -1/4 I epsilon, or just z of I over 4 epsilon. Okay. But this is just now a low temperature partition function, right? I am just now, you know, I mean, that's like back here with just beta here, right? And so it's controlled by the Casimir energy of the ground state, right? Because the low temperature partition function should just be e to the minus beta times the Casimir energy. Okay. And of course, that's known in any CFT. You can compute it using the conformal transformation from the plane to the cylinder. So that's the cardiology. And so then indeed, this is just pi squared c over 6 beta. Okay, so that works. So this funny saddle point that we constructed is the dominant saddle point contributing to this calculation. Yeah.
Sorry, can you remind me the difference between the pseudostates and the standard canonical
Well, you see, there's the e to the I pi j here, right?
Yes.
That's the difference.
Oh, I mean, grand.
Oh, you mean for angular momentum?
Yeah.
Good. So let's comment on that, right? So indeed, so whenever I show this to people, the first question is always, shouldn't the saddle point for this be the rotating BTZ with an imaginary chemical potential, right? Because this is an imaginary chemical potential for angular momentum. And so that is a saddle point that contributes, but it's subleading to this one.
Oh, so the curved solution is like.
It's subleading, yeah. Yeah, this is the dominant saddle. Now, I just want to mention in words, you could complain, I mean, come on, Daniel, this is a Euclidean calculation. And this whole issue of whether there's things are time-orientable or not is a Lorentzian issue. In the end here, I just ended up with a torus, which is, it seems like a fine, you know, solid torus, it's orientable geometry, okay? So to really argue in Lorentzian signature that this geometry is here, I have to do something slightly more, which is in this pseudostate compute correlation functions and continue them to Lorentzian signature, okay? And then see if I can really match the Lorentzian correlators in the pseudostate of this Lorentzian geometry that's not time-oriented. So I'll just say that works, okay? It's a little tricky because, you know, I can't actually do the CFT correlator calculation, right? Because I'm not good at strongly coupled CFT even in 2D. I think if I were better at the torus Virasoro identity block, I could probably do the calculation. But we were lazy. We just did the calculation in the Ising model with the excuse being that in this regime, the correlator should be universal. But then anyway, we see it matches the bulk calculation here.
I'm actually confused with this question. So, I mean, from the boundary point of view, the special, you chose to with tau. So I thought that people have computed such things using the Euclidean BTD that with the rotating.
No, but that calculation is usually done where this is real. So because as I discussed, where this is pure imaginary. If you want to get the rotating black hole, what you want a real coefficient here, because you want to bias the ensemble towards states with non-zero angular momentum, right? This doesn't do that. It's just a phase.
I see.
Yeah. So people are very good at the case where you put something real here.
I see. So that was the case you would say that those would be.
Yes.
The eyes will change.
Yeah, the eyes are changes. And actually, it matters that it's pi here. If you put 2 pi, then it's BTZ again.
What is the CFT interpretation and I-type interpretation?
Well, it's this, right? This is a well-defined thing in the CFT.
Okay. It's just a particular, it's just a particular tile.
Yeah,
So it's nothing special about it. It's just.
yeah. In the CFT, it's a totally kosher thing.
Okay.
The surprising thing is that in the bulk, it's dual to something crazy.
I see.
Yeah.
Okay.
Yeah.
And you mentioned that the different PPTs will contribute for a sub-meeting order, but shouldn't it not contribute because it has like the different PPTs from real language?
How's what?
Real language.
No, you analytically continue, Daniel Monet.
Oh, you got it.
You analytically continue to imaginary complex potential. Imaginary chemical potential. Yeah. Okay, I don't want to go too much longer. I feel like we've already gone for a while. So I just want to make one other comment and then I'll stop. So here we discussed quantum gravity in ADS. I want to discuss quantum gravity in a closed universe and see what this has to say. Okay. Now, let me begin by making some general comments about gauge theory in a closed universe. So for example, electrodynamics, right? So if you do electrodynamics in a, say, a spatial sphere like S3 or something, right? Then the total charge of the universe is 0, which is a consequence of integrating Gauss's law over the sphere, okay? As we discussed earlier, when you gauge a discrete symmetry, the same is true, right? You're supposed to project on the singlet states in both the twisted and the untwisted sector. And the same is true for gauging anti-unitary symmetries like time reversal or CRT. In the case of an anti-unitary symmetry, however, this has a rather surprising consequence. And so that's what I think I'll leave you with. So say that psi and phi are invariant under some anti-unitary symmetry, theta. So then let's consider what happens if we have a superposition of psi and phi. So let's look at theta acting on A psi plus B phi. Well, since this is anti-linear, we get A star times psi plus B star times phi. And in general, this is not equal to the state that we acted on. Okay. So what this tells us is that theta invariant states form a real vector space. We're only allowed to take superpositions with real coefficients. Now, in my understanding of quantum mechanics, or certainly my understanding as of a year ago, the Hilbert space is complex. Okay, many of the standard predictions of quantum mechanics, the double slit experiment, the functionality of Shor's algorithm, at least in the way that I learned them, they certainly rely on phases in the amplitudes. But here I'm saying that for quantum gravity in a closed universe, there are no phases. Only real superpositions are allowed. So in some sense, this is a modification of quantum mechanics. Now, you may be looking at me saying, come on, Daniel, that's ridiculous. After all, we could be living in a closed universe and we tested quantum mechanics many times. And okay, we probably haven't run Shor's algorithm yet, but we've certainly done the double slit experiment and it works. Okay, so what's going on? Am I saying something wrong here? And my claim is no. So in fact, in some sense, there is a way that I can take all the experiments that we've done with quantum mechanics and fit them into a real Hilbert space. So let me first tell you how to do that. This will be the last thing I say, and then make some comments about what it means. So the basic idea is that anytime you're doing quantum cosmology, meaning quantum gravity in a closed universe, To define observables, you need some kind of clock to tell you what time it is, what the time is where you're doing the observables. Now, and the same is true for time in situations that involve time reversal, but the clock can be a bit simpler. It just needs to be a two-state clock that tells you whether time is going forward or backwards. So let me say what that means in practice. So say I have some system S in a closed universe, and I want to prepare it in a state psi S, okay? Where that state may involve complex coefficients in the superposition, because it could be an atom or something, right? Something that we've done experiments on where we were certainly able to do complex coefficients. Now, there's a way I can make a state which is theta invariant, let's say CRT invariant. The idea is I take the tensor product of this with the state of the clock that's going forward in time, and then I prepare a superposition with a state where the clock is going backward in time, and then I act with the symmetry just on the system to reverse it, right? And so now this is a CRT invariant state because CRT flips the direction of the clock and it exchanges these two states. Similarly, say I want to do a measurement to see whether or not the system is in a state chi, all right? Well, that's not T invariant, or CRT invariant, but I can make something that is by saying I do an experiment where I check if the clock is going forward in time, and if so, then I check if the system is in the state chi. But then I also have to check if the clock is going backward in time, and if so, then I check if the system is in the CRT conjugate of chi. All right, and this is again a CRT invariant projection. So this is a state in a real vector space. This is an operator on a real vector space. But if you compute, and so I won't do the algebra, but it's easy, you can check for yourself, the expectation value of this, I just get what the Born rule would have told me to do, which is I take the overlap of the two states in the complex Hilbert space of the system X, and then I take the absolute value squared. So I can reproduce that calculation in a real vector space. Okay. Now you may be saying, well, come on, Daniel, this is kind of bookkeeping, right? What I just showed you is that I can take any quantum system with a complex Hilbert space. I can add 1 degree of freedom, which I call the clock, and then I can lift all the calculations in that system to real calculations in the larger Hilbert space, including the clock. All right, so from that point of view, it's bookkeeping. That's something that you can always do. All right. But the key point is that this set of manipulations required me to be able to define the symmetry acting on the system alone. And if the universe is really finite size, then there won't be a symmetry that just reverses the system and not the clock, because there will be interactions between the system and the clock, and it won't be a symmetry to reverse one and not the other. Okay. So this manipulation relies on me being able to sort of move the clock infinitely far away from the system so that I can define symmetries that act on the two separately. And so there will really be corrections to this calculation if the universe has finite size. And those corrections you won't be able to understand without going to this Hilbert space, which is real. So the claim is that the reality of the Hilbert space introduces corrections to quantum mechanics, which go away in the limit that the universe becomes large. Okay. Now, I should say that in electrodynamics, there's something perfectly analogous to this that happens, right? Say I'm living in a sphere universe, and I want to measure 2 to 2 electrons scattered. There's this inconvenient fact that I can't make a state of 2 electrons because it doesn't have 0 charge, okay? And the way you fix that is you put 2 positrons on the other side of the universe to soak up the flux. And then locally you do 2 to 2 electron scattering, and you get something that's not quite the S matrix, but it's not too different from it if the universe is big. So here the clock is playing the role of the positrons on the other side of the universe in that experiment. Okay. Now, of course, we're never going to measure any of these corrections, right? Even, because we don't even know, maybe our universe is infinitely big, right? So this is not a measurable thing. But I think it's a very strong constraint if you want to try to come up with a theory of quantum gravity in a closed universe, like a holographic dual of quantum gravity in a closed universe, because it's saying the Hilbert space has to be real. So somehow the structure of that theory must be such that it forces the Hilbert space to be real. Which is to me fairly surprising. Okay, so I think I'll stop there. We've definitely gone on long enough. So thank you everyone for listening. Happy to take more questions.
Thank you, Daniel. Question from the audience? Also online audience.
Yeah, please. Yeah.
Sorry, maybe please let me think after my previous question again.
Yeah.
So we use technical to define the pseudo states.
Yes.
On matrix, like manifolds.
Yeah.
What I was asking that, like, say, assume this rho is an anti-linear operator. Then you can also write it into a matrix by
No, but rho is a linear operator.
like
I define it to be, so when I define it, it's right, like this rho is a linear operator. It's a positive times a unit.
yeah, I mean in this example, like,
Yeah.
but how about like defining from the technical of a matrix?
So I think you have to make a choice. So, I mean, you see, the formula I got for rho in the CFD was also linear, right? Because there were two anti-unitary operators, right? So it made a unitary operator.
Sure.
So I think you can't stop me from just defining the operator by giving you its components in a basis.
I see. So
That's just my definition.
a kind of short.
Yeah.
I see.
Yeah, I think if we tried to make it anti-linear, we'd probably get really confused. In principle, we could, but I don't know if there would be any nice calculations.
I see.
I have a question.
Yeah.
So I don't know whether this analogy is right. So, sometimes we may start with maybe system with fermions and with Hilbert space. Then the fermions can be complex. The Hilbert space can also be complex.
Yeah.
But sometimes we can rewrite a complex fermion as a two real
Yeah.
fermions. For example, a lot of modeling T-TED, you write one
Yes.
complex fermion, zero dimension to as a
Yeah, but
size.
usually we say the Hilbert space is still
That's-
complex.
Okay,
Right?
that's right. So I was wondering, so that's not the analogy you are trying to make, right? You are really trying to make a Hilbert space
Yes,
real.
I really want the Hilbert
Right,
space.
but
to
then
be
I'm confused by one thing though. So in the usual topological phase, matter like grading process, you do want to measure something like barrier phase, which is complex, a complex phase. So what does this type of context mean? Like,
No, but I think everything you measure in the end is going to be the expectation value of a Hermitian operator.
Okay,
I think that's just true. That's
Okay.
quantum mechanics.
okay,
It's, yeah, the Berry phase, maybe it's like the entropy or something, right? There are lots of things in quantum mechanics that are computable, but not measurable directly.
okay,
To me, measurable really means like, here's the, I have one copy of the system in the lab and there's some experiment I'm going to do to get a result. And you can't measure the entropy like that. Yeah.
So
Yeah, you can probably
so
try
for
to-
example, like even the electron, like the double slit experiment, maybe you are say in a quantum mechanical way, we are having some complex interference, but in the end, we want to measure some amplitude.
Yeah, in the end, the answer is a
It's a real
probability,
amplitude.
right? Yeah. Yeah, this probability is all you ever actually measure.
Okay. Thank you.
Just a very, very random comment, like a direct consequence that the Hilbert space is real.
Yeah.
Is that this kind of system can be efficiently simulated on classes.
I don't think that's true.
Like why? I mean, if you use stable, like the universal bit set and only,
Well, sorry, because you'll still have a sign problem because it's real, but you can do superpositions with either sign. So you'll have to compute overlap, to compute evolution and so on in the Hilbert space. So it'll be orthogonal instead of unitary.
Yeah.
But there'll still be signs that can go either way. So yeah.
So you mean like the difference between plus and minus, like effectively acts as a TH, like.
Something like that, yeah.
This-
Yeah. I think in order to be easy classically, you need to make it positive. Not just zero.
I see.
Yeah.
That makes sense.
Okay, great.
I had a small technical question, just like, can you explain again the procedure of just like this adding the background?
Yeah,
The discrete gauge field, the holonomy, the line that went through.
oh, yeah, okay. You mean, so I mean this example or in general? So it's,
Well, maybe that example.
yeah, so an example, the idea is I wrap the symmetry operator, so that this is a codimension, this is dimension d-1 operator. It's codimension 1.
Yeah.
Right, so then I take the cycle, the one cycle where I want there to be a holonomy, and I find a Poincare dual cycle. And then I put this on the dual cycle. So here it's obvious what the dual cycle is because I do the cylinder. I guess to do a general manifold, then you have to use the theorem that there is a Poincare cycle to know that there's some cycle. Yeah, and then the only trouble is that there could be in general, there'll be intersections between the groups, and you have to say something about that, and that's where you could have the null.
Makes sense.
Sure.
I think we should thank Daniel again.
Yeah.
I want to thank you. Let's conclude this.
Do you guys have lunch after this, by the way? Or-
We have a member seminar, so we can go upstairs. Just
Oh, so there's
there's
food upstairs,
Yeah, there's
yes.
a member seminar. Dinner will be separate.
Yeah.
By the way, if you guys want, you can join the dinner.
Sorry, Dan, I'm a bit slow about this. Can you explain again the density matrix? Why is it that you do the upper right or lower left?
Yeah, there's-
Well, I wanted to
You want
define,
to-
I just wanted to define a state. With
Send me an
analytic,
email
you know,
first and I'll put the time. Maybe.
And I mean, one way you can think about it is there's certainly a thing I can do,
We can meet at the
because I
restaurant.
can compute Euclidean correlators
Okay,
of the various spheres.
Sure.
And analytic around
6:30 or 7.
Okay,
I think we depend on it.
Okay.
So I was trying to say in the
Thanks for
Hilbert
saying
space
that.
language what that
Send me an
is.
email. 6:30 or 7.
Okay.
We'll meet at the restaurant.
That's what you usually do when
Just
you
near
define a Euclidean state.
Harvard Law School.
Yeah. Okay, so
It's,
the Euclidean Mobius strip
It's on the street next.
looks like this,
Thanks.
right?
Thank you.
Yeah. But then if I want to give it a Hilbert space interpretation, I have to cut it.
Yeah.
And then I get this.